In the audio world, there are two general types of signal paths from a wiring standpoint: balanced or unbalanced. This actually applies to both the analog and the digital realm. For now, I will stick to the analog world. In the analog realm, unbalanced, which are also called single-ended audio signals, generally should be used only for short distances, like maybe 10, 15, maximum 20 feet, and even that's pushing it. Examples of unbalanced signals and connections are RCA connectors, quarter-inch guitar cables, and stereo mini connectors, as you might find in an iPod or something similar. Most consumer audio equipment, which we still sometimes use in the professional world, like CD players or Blu-ray players, or maybe the odd occasional VHS deck, why I have no idea, or an iPod or laptop, similarly are unbalanced in their output. Most electric or electronic musical instruments, like synthesizers and similar things, are also typically unbalanced. There are two main issues with running unbalanced signals long distances. The first has to do with what's called common mode rejection, or CMR. This means that unbalanced cables do not do a very good job of rejecting unwanted interference from electromagnetic fields, also called EMF. This includes power hums from electric cables laying on the floor, AM radio stations, cell phones, electric motors, anything of that nature. This diagram shows approximately what happens with an unbalanced signal. You have two conductors inside of an unbalanced cable. The center conductor being the signal part of it, and the outside shield or braided shield is as described, a shield. The shield is the ground connection. With only the one lead going inside of it, any noise that's picked up arrives at the other end and is amplified. Most of the time, unbalanced outputs and inputs are very high impedance, typically 10K ohm, 10,000 ohms, and sometimes more. For something like an electric guitar or bass, it can be 25K to 150K ohms, sometimes more depending on the type of pickup inside of the instrument. Every type of cable has an inherent cable capacitance. As I described in the last episode, capacitance in a circuit is a factor in impedance. And what is the mantra? Frequency is a factor of impedance. So, if you have a really long, like a 50-foot guitar cable, plugged into your guitar and into the amplifier, it might sound off color or dull or thin even, depending on the pickup configuration in the amplifier, when compared to a shorter cable plugged into the same two devices. There are actually some interfaces for guitars which allow you to adjust the input impedance coming from the guitar to better match the guitar's impedance, which produces a more desirable tonal quality. This particular tube DI made by Summit has a tube preamplifier circuit in it and has a knob called loading, which is used to do exactly that. Balanced audio signals use a pair of wires with an outer shield to send signals between devices. These are also referred to as twisted pairs or simply audio pairs. The idea is this: an output from X device, in this case a simple microphone, is sent 200 feet down an XLR cable to a mixer. Within the audio pair, there are two wires. One carries an in-phase or positive signal. One carries an out-of-phase or a negative signal, as it's often labeled. While the original signal from the source is passed through intact, any induced EMF or other noise is canceled out at the receiving end, at the mixer's input. This illustration further demonstrates that. As with any other cable, balanced audio cables do have some inherent cable capacitance, but it's not as severe as unbalanced cabling would be. When you look at the specs for a typical spool of balanced audio cable, the raw cable, like if you were to buy 500 feet of it, it will state a specification in capacitance per foot and resistance per foot. The longer any analog cable gets, the more it will attenuate, which is part of the resistance component of it, or will color the sound because of capacitive buildup. There are some exotic cables that use unusual materials like silver tellurium conductors and Teflon insulators and stuff like that that get around that to a certain degree, but they're also ridiculously expensive, and the only people buying that kind of thing are some high-end recording studios and audiophiles with way too much money to burn. But wait, there's more. Since we're on the subject of balanced audio, we have to address the basics of phase and polarity. There are some semantic arguments about how those two terms are used, or sometimes overused. As described earlier in this exciting episode, a balanced audio signal carries an in-phase and an out-of-phase signal. In this particular case, those signals are truly opposite in polarity. If you were to take the two wires at the end of the XLR cable, twist them together, and connect them to something, you would find that the audio coming from the other end would be canceled out, and all you would have left is the hum and buzz or any induced signals that were picked up along the way. This is kind of how that amplifier circuit works as described in the prior diagram, in the fact that it combines the two signals and ignores the noise. An XLR connector, as shown in this diagram, has 3 pins. Pin 1, as labeled, is always the shield, or in some cases, the ground, as it's often called. Pin 2 carries the in-phase or positive signal, as is often labeled. Pin 3 is the out-of-phase or negative signal, as is often labeled. Let's use an example of how not to wire an XLR cable. If one has a stereo mini connector, like for your iPod or your laptop or something of that nature, that you want to plug into a mixer, particularly anything else with a balanced input, you cannot simply wire the 3 terminals of the stereo mini connector to the same 3 terminals or corresponding terminals on an XLR connector, as in this example. Instead, it needs to be wired in this example on the left side of the drawing, or like this. This is a stereo mini to 2 XLRs connector. The previous drawing was for a stereo mini to mono adapter. In the example of doing it the wrong way, if you take the left output from the iPod, wire it to pin 2 of the XLR, and take the right output from the iPod and wire it to pin 3 of the XLR, what you will hear typically is, depending on the era of the recording, either a thin, slightly distorted sound coming out, or a ton of reverb and effects and no vocals, or just a massive amount of reverb and instruments with no vocals. It has a lot to do with how the project was mixed and when it was done. A lot of old 60s crooner style songs, Andy Williams and things of that nature, you'll find if you try to cancel those out that way, you'll get a lot of reverb and not much else. In the correct wiring illustration, shows what's basically a stereo to mono adapter, and the second part of the drawing shows a stereo to mini stereo XLR's adapter, or the other option is to use a stereo DI box, which can interface these type of systems. And here are some examples of what those sound like. Here's the first example of the incorrectly wired stereo mini to XLR mono. In the second example is the same source material with the stereo mini to XLR mono wired correctly. And the third example is the stereo mini to dual XLRs, stereo, or using the stereo mini through a stereo DI or direct injection box. Most serious professional audio consoles will have what is referred to as a phase or polarity switch on its inputs. An example of where this can be useful is a situation where you have a performer playing an acoustic guitar with a pickup and you want to add a mic to the outside of the guitar to create a certain tone. Most of the time, like 90% of the time, the pickup will be out of phase with the microphone. If you combine the two sources, you will notice that they start to sound kind of thin or strangely colored. That means that they are out of phase, or in this case, out of polarity with each other. If you take two of them with equal volume and bring up the two faders to the same level, and notice that as you drop one away or boost one up, whatever the case is, it will start to sound correct. The solution is to reverse the phase, or reverse the polarity, as is correctly termed, of one of the sources. It doesn't matter which one. And then try the same test. In these examples, you can see how that works. We have an acoustic guitar that has a built-in pickup connected to a direct box and a high-quality condenser microphone on the outside of the body combined. In the first example, you hear them as they are with a normal phase relationship. In the second example, we have flipped the phase, or flipped the polarity, using the built-in phase switch as is labeled on the guitar itself, which was obviously put there for that very reason. Semantics. Many will argue that the phase switch is not really a phase switch on the console. It's actually a polarity switch, as a true phase adjustment is a much more complex adjustment. This is true from the standpoint that this particular switch only corrects for things that are 180 degrees out of phase, and does little or nothing for something that may be 45 or 90 degrees out of phase. Those situations occur if one source is heard between two closely positioned microphones due to differences in arrival times. If you'll recall the earlier illustration of wavelengths versus distance that vary by frequency, as wavelength is a function of frequency. In this first example, we have two microphones roughly 2 feet apart with a demonstration of mics in phase, and this sample with the mics out of phase. This is a demo of two microphones mounted at an odd spacing from each other. This dynamic microphone mounted pretty close, and this condenser somewhat further away. This is the sound of my voice equidistant to the two. closer to this one, closer to this one. This is the voice somewhat off of both of them, which should establish the phase relationship. Here are the same two mics with one intentionally thrown out of phase, so you can hear the difference. 1, 2, 3, 4. These are only spaced about 2 feet apart. Here's the same test again with the mics about 4 feet apart. Equidistant between the two. 1, 2, 3, 4, 5, 6, 7, and 8. Closer to the handheld mic. 1, 2, 3, 4. And closer to the condenser. 1, 2, 3, 4. Check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the same test again with the dynamic microphone inverted in phase. Same test again with dynamic phase reversed. Of course, you won't be able to tell that right on the microphone, but you'll hear it as I get further away, and you hear me equidistant between the two mics. As I get close to this, you'll start hearing that. 1, 2, 3, 4, 5, 6, 7, 8. Okay, this test is... This is a demo of the two microphones, one at a time. Here's the first microphone, the dynamic handheld. Second microphone, the little condenser. Here are the two side by side, so you can hear the difference between the two in terms of phase. Here's the phase relationship between the two. 1, 2, 3, 4. Okay, here's the same demonstration with the phase flopped on the dynamic handheld. Dynamic microphone by itself, condenser microphone by itself. The two of them side by side. 1, 2, 3, 4. Another situation where these more subtle phase variances come into play is where you have a source being fed out of your mixer. It's also being sent to an effect device or some other process. It could be a recorder or something. And you've brought that recorder or that device back into the mixer and then recombined it with the original source. Because of the latency in that device, you wind up with some comb filtering because of the slight offset between the two. This is an example of something that may be only 45 degrees out of phase or 90 degrees out of phase because of the slight timing change between the two sources at that point. Learning to identify what that sounds like is a key to troubleshooting such problems as they arise. In this first example, we have the original material. In this second example, we've taken the same signal and then added another copy of the same signal and offset it by a couple of milliseconds to simulate going through another process or something that might cause this type of phase issue. So you can very clearly hear the comb filtering in the two sources combined. Along with that, here's an illustration of what that looks like on an oscilloscope.
But wait, there's more.
If your mixing console doesn't have a phase or polarity switch, if your amplifier doesn't have a phase or polarity switch, for $49.95 with shipping and handling fees of $49.95, you can have one of these handy-dandy Shure pocket phase switch barrels. A very handy thing to keep in your toolkit to fix simple phase and polarity issues. That's all for this episode of Mr. Warren's Audio Hood. Please join us again next time for the next exciting episode of Mr. Warren's Audio Hood.